Good evening, student. Today we are going to discuss about the resonant tunneling. The first thing we want to understand what is the tunneling, because already we have discussed in the first semester what is the tunneling on the basis of the quantum mechanical Schrödinger wave equation. We already derived that expression, then we saw what do you mean by tunneling. We have to look up once again what is the tunneling. Then we have to move into the topic what do you mean by the resonant tunneling. So the resonant tunneling we will see, then its characteristics also we want to know which device the resonant tunneling can occur, and what are the device applications using the resonant tunneling, and then what is the characteristics of the resonant tunneling. Those things we are going to discuss that today topic. So we can ask one question. What do you mean by the tunneling? What is the tunneling in general? We can ask. We are not going to derive any quantum mechanical equation. Just we are going to look at the quantum particle. What is if it is happening? What if it is approaching the barrier of certain potential? Suppose here we are taking the one quantum particle, incoming particle of energy E. You can take this incoming particle of energy E, this energy. It is approaching the barrier of potential V naught. What would happen when it is hitting on the barrier? Just look at the diagram once again. It's incoming. When it is hitting the barrier, there is a probability of transmission of the particle as well as the reflection. It is happening simultaneously. So there is some probability. So you can call the transmission coefficient plus the reflection coefficient, and net should be equal to 1. That means some probability it can tunnel, so with some probability it can reflect. That is the meaning. Suppose if I am sending like a same electron like 50 times or 60 times, so if I am observing each and every time, there is some probability. Sometimes it can transmit, sometimes it can get reflected. That is a quantum mechanical phenomena. The tunneling means if you are sending the quantum particle with the energy E to the barrier some height V naught, so it can transmit some part of the energy, then some part of the energy it can reflect back. That means after transmitting, the amplitude is reducing, then reflected wave amplitude also it got reduced. So this is the meaning of the tunneling on the basis of the quantum mechanics. Now we are ready to answer the question, the what do you mean by the resonant tunneling? So here we are going to look at the definition, then we will discuss using the diagram. So the resonant tunneling refers to the tunneling in which the electron transition coefficient through the structure is sharply peaked about a certain energy. That is called the resonant tunneling. That means if you are look at the transmission coefficient, suppose if you are drawing the transmission coefficient in the y-axis, you can call it's a transmission coefficient. The x-axis represents the energy. So what would happen? The transmission coefficient only at a certain energies it can peak. That means only the certain resonant condition, if it is matching, the electron can tunnel through the material, given quantum material. Suppose once if you are taking the quantum structure, if it is a quantum well structure, so in the quantum well structure, if you look at this region, this is a well region, it is having this discrete energy. The energy level for this region, if you look at, it is having like the energy level diagram. It is looking like that. That means it is having well structure. So in the conduction band, it is having the discrete energy. There is a probability of occupying the electron. In the valence band also, it is having discrete energy. There is a certain probability only the allowed electron can be occupied. If you are sending some charged particle like a electron through this, or holes or electrons through this, this is electron, this is holes. If you are sending some electromagnetic radiation, not electron and holes, just it's wrong. Suppose if you are pick up the one photon of energy h nu, if you are sending this energy to this through this potential wealth, if it is matching with a certain mm, energy level, then there is a transmission, there is a absorption will happen. Then there is a transmission of the charge carrier also. Suppose if you are using this quantum device. Suppose if you are sending the electron or holes by giving or by biasing this material, or if you are giving some forward or reverse bias to this material, or if you are biasing this material, what would happen to this charge carriers? It can either tunnel or it can deflect back for the certain biasing condition. That's the thing we are going to look up the next slides. Before that, we want to discuss what are the important characteristics of the resonant tunneling. Then we can move the exactly what is the resonant tunneling diode, how the peoples are using the quantum well structure as a resonant tunneling. That's the thing we are going to look at in the last slide. So, what do you mean by the resonant tunneling diode? Which device we can call the resonant tunneling diode means the quantum well structured device, or the quantum well structure we can call that is called the resonant tunneling diode. It can be like either it is made up of the aluminum gallium arsenide on the top as well as the bottom layer. The center layer it can be made up of the gallium arsenide, the low bandgap material. That structure we can call the quantum well structure. That device we are going to use as a resonant tunneling device. So what would happen in the resonant tunneling diode means we can see then the negative differential resistance. According to Ohm's law, if you are plotting the current voltage characteristics, that means I versus or V versus I, what would happen? There is a linear relationship because we have V equal to IR. This is the Ohm's law. So it is having the positive differential. That means the slope of the curve is positive. That is a positive differential coefficient. You can call it's a di by dv. So that you can call it's equal to the resistance. So it is having the positive value of differential coefficient. But if you look at the resonant tunneling diode, we have the negative differential resistance. We will see how that negative differential coefficient is happening. We will see that in the next slide. Then the next characteristics for the certain applied voltages, increase in the voltage led to decline in measured current. That is the thing. That's the meaning of the negative differential coefficient. Because if you look at this diagram, here if you are look at this diagram, what would happen here in this diagram? If you are increasing the voltage, there is a current also, it is getting increased. It is represented by the graph. That means there is no decrement of the current according to this Ohm's law. But in the resonant tunneling diode, what would happen? If you are increasing the voltage for certain applied voltage, increasing the voltage led to there is a discrete in the current. So that the thing we can call the negative differential resistance. We will see in the next slide how it is happening. Now the potential application for the quantum wave structure or resonant tunneling diode is it can be used as a high frequency oscillator as well as the high speed switching. High speed switching means you can switch the device within the nanosecond or within the picosecond. You can switch the on state to off state as well as the multi-level logics. We can use this device. Here, look at the diagram. This center diagram represents the quantum well structured diagram. That means you are seeing the two barrier. That means the electron is approaching the two barrier. The left hand side, we are taking the some semiconducting material. It is having the lot of electrons in this region. With the Fermi energy, you can call this is a mu L. The topmost energy level is called the Fermi level. Then the lowest uh, uh, energy level of the conduction band is EC. Then uh, here if you look at the right hand side diagram, there is a topmost energy level of the conduction band. You can call it a because it's a mu, or right hand side you can call it a mu, or this is a Fermi level. Then the bottom of the conduction band it's EC. Then there is a, in between there is a filled it's filled by the electron. So here we are taking one semiconducting material. In this region also we are taking one semiconducting material. So in between these two semiconducting material, we are placing the quantum well structure. This structure is called the resonant RTD. In general, it is called the resonant tunneling diode. How did it happen, the resonant tunneling? That is the question we can ask. Here we didn't show that the uh, valence band of these two semiconductor, then how the whole tunneling is happening we didn't see. Just we are going to look at what would happen on the top of the quantum well. We are not going to discuss about the bottom of the quantum well. Whatever we are discussing to the electron current, then the same thing would happen to for the whole current also. Here, what would happen if you look at the inside the well? This is a one barrier. You can, it's a high band gap material. You can, example, you can take the aluminum gallium arsenide. The center one is you can take the gallium arsenide. It's a low band gap material. That's why the it's looking like a well in between the. In this one also, it's also aluminum gallium arsenide material. So the center one is it's a gallium arsenide. This is a, you can call gallium arsenide. Inside the potential, we are just taking the one discrete energy. That means this is the energy is allowed for the electron. If the electron absorb any energy, it can go and it can sit at the energy level, but it can't, there is no allowed energy above as well as the below. So suppose what would happen, the first initially we are applying to this structure less voltage. Here see, up to the certain voltage there is no current at all. See here, up to certain voltage we are looking the y-axis, there is no current. That means it is zero current up to certain voltage. After increment of the certain voltage, see here, what would happen, the this energy, the discrete energy inside the quantum well, it is coming down. That means the level will change according to the bias. If you are giving the bias such that the level will be decreased, that means the this energy level here, if you look at this energy level, it's going down, as well as at the same time this energy level is going up. At the if you look at the center energy level, this is the discrete energy level inside the quantum well structure, it's also going down. So there is some probability of the tunneling for the electron from the left hand side. That means here there is lot of electron. So what would happen, this Fermi level, this is the topmost level for the left hand side semiconductor. This Fermi level is matching with the discrete energy inside the potential well. So what would happen, this electron can see there is a equal energy inside the well, so it can try to tunnel through this barrier. So because of the tunneling here, the electron, it can go from this Fermi level because equal energy, so it can tunnel through this region. It can go as well as sit in this region, then it can tunnel. So because of this tunneling, we can see there is a slightly rise in current through this. After increasing the certain voltage, there is we can get the some few amount of current. So we can observe the current is getting increased due to the charge carriers is tunneling from the left to right. So if you are increasing again the beyond this voltage, what would happen, if you are increasing, there is a discrete in the current. Why it is happening means, after increasing the certain voltage, here if you are here see, this discrete energy, it is matching with the bottom of the conduction of band of the left hand side semiconductor. So there is a large current. This large tunneling is happening. Large charge carriers, electrons can tunnel through the barriers. So you can observe this the bigger arrow, the dark red arrow represents the huge amount of current. That's why it is showing, it is shown here at this voltage there is a huge amount of current. Even beyond this voltage, if you are giving to this suppose if think if I am giving the like this kind of voltage, this to this structure, what would happen after here, it's not a fixed voltage, we are giving the variable voltage here. Beyond the this voltage, the high current voltage, even after if you are increasing the voltage, this level, look at this level now, you can call this voltage is like a VP at the peak voltage. This level is matching with the EC, but beyond the VC, this VP, the peak voltage, if even if you are increasing this voltage, what would happen? this level is going down. Previously it was here when the voltage is Vp. Beyond this Vp, if you are increasing beyond the Vp voltage, the level is going down. That means there is no charge carrier here. So that means there is now there is no electron available to tunnel the barrier. That means there is a level, but we don't have any charge carrier in the left hand side. That means we are in the region, the this level, it is seeing the region, the empty state region, the forbidden region. So there is no tunneling. The tunneling is not allowed here. Here also is not allowed. But you can observe the few charge carrier, because that's why there is a sharply decrement in the current. After, even if you are increasing the current, the level go down here. Then there is a charge carrier even at the bottom of the here. I didn't show that the valence band here. So if you see the valence band, the structure also, it will be looking like that. So there will be a here valence band, here it should be valence band. So once the level is matching the valence band, then the charge carry tunneling will happen after a certain voltage. So from these lectures we saw the this slide, we understood what is the resonant tunneling diode. There is a quantum well structure. Before the quantum well, there is a semiconductor. After the quantum well, this combination will form the resonant tunneling diode. Inside the diode, there is a discrete energy level. Whenever the discrete energy level is matching with the left hand side, the Fermi energy, or the EC, the lowest energy of the conduction band, there is a tunneling current. It will increase even if we are increasing the voltage. So if it is not matching, then there is no tunneling. The Fermi level or EC, if it is not matching, the level is going down. The center potential level, if it is going down, there is no tunneling, means there is no charge carrier available to tunnel that energy level. So the current is decreasing. So this is this region here. I want to say one more thing. Here up to this region, there is a positive differential of the current voltage relationship. But here, look at this diagram. Here you can see the negative differential. This is a negative resistant region, or negative, you can call this is a di by dv. It's a negative, or this is a negative. It won't obey the Ohm's law. This is a negative differential region. So this region can be used as a high frequency oscillator on some logical switches. So we saw the one more applications. So this is our end of lecture.